Welcome to a video on the principal unit normal vector. A unit normal vector is a unit vector that is orthogonal or perpendicular to a unit tangent vector. It also points in the direction that a curve is turning. Remember that the unit tangent vector points in the direction an object is moving. So for example, in this graph, the orientation of this purple plane curve would be in this direction, and notice that the red unit tangent vector points in the same direction as the orientation of the curve. So we'll label this vector t, and this blue vector is a unit normal vector, and notice that it is orthogonal to the unit tangent vector. Let's take a look at this in space. In this graph we see a space curve in blue. The red vector is the unit tangent vector, and this purple vector here is the unit normal vector. And notice that as t increases, those two vectors remain orthogonal or perpendicular to one another. So again, the purple vector is the unit normal vector, and the red vector is the unit tangent vector. Here's how we'll determine the unit normal vector. First, we'll have a smooth curve defined by a vectored valued function in R2 or R3. Then the principal unit normal vector is defined by the vectored valued function n of t is equal to t prime of t divided by the magnitude of t prime of t. Remember, the vector valued function t of t is the unit tangent vector valued function. So to determine the unit normal vector, we'll first have to determine the unit tangent vector and then find its derivative. And sometimes this can be challenging because t prime of t and the magnitude of t prime of t can be a bit challenging to determine. So there is a shortcut if the unit tangent vector is in a plane. What I mean by that is, if the unit tangent vectored valued function only has two components, then there's an easy way to determine the unit normal vector. The way we do that is we interchange the x and y components, and then we either change the sign of x of t or we change the sign of y and t. And the way we determine that is, remember that n of t must point in the direction that the curve is turning. Now the reason why this shortcut exists is, remember in algebra that if we have one line that has a slope of 2/3, if the second line is perpendicular to a line with slope 2/3, the slope would be the negative reciprocal of 2/3, or negative 3/2. So you can think of the numerator as the y component and the denominator of the slope as the x component. So if we switch them and then change the sign of one of them, the vectors would be perpendicular or orthogonal. Let's go and take a look at a couple of examples. When t is equal to 1, we want to determine the unit normal vector. So this is what we want to find when t is equal to 1. But before we determine the unit normal vector, we first have to find the unit tangent vector valued function, as we see here on the left. So let's start by doing that. So the derivative of r of t would be 3t squared for the x component and 4t for the y component. When you divide this by the magnitude of this vector valued function, so we'd have the square root of 3t squared squared, that would be 9t to the 4th, plus 4t squared would be 16t squared. So if we want to, we can rewrite this so that the x component would be 3t squared over 9t to the 4th plus 16t squared, and then the y component would be 4t divided by the square root of divided by 9t to the 4th plus 16t squared. Now notice that the unit tangent vector is only going to have two components. So in this case, we're going to take that shortcut that we mentioned just a minute ago. So let's go ahead and evaluate this at t equals 1. So we'd have 3 times 1 squared, that would be 3. And when t is equal to 1, we're going to have the square root of 9 plus 16. That's going to be the square root of 25. So this will be 5. And over here, we're going to have 4 over 5. Now what we're going to do is take the shortcut to determine the unit normal vector when t is equal to 1. Remember, the shortcut says first what we do is interchange the x and y components. So 4/5 will be the x component, 3/5 will be the y component. But now we still have to determine whether we should change this to a negative or this one to a negative. To determine that, let's go and take a look at the graph of this space curve and also the unit tangent vector at t equals 1. So here's our space curve, and it would be traced out in this orientation. We know that because the unit tangent vector points in that direction. And remember, the unit normal vector points in the direction the curve is turning. It's turning to the right, and therefore the unit normal vector will have to point to the right. And that tells us that if this vector was in component form, the x component would be positive and the y component would be negative because it points to the right and also down. So that tells us we must change the sign of the y component here. And now that we know this, we could determine the unit normal vector valued function by interchanging these components and then changing the sign of the y component. So the x component would be 4t over the square root of 9t to the fourth plus 16 squared plus 16t squared. And the y component would be negative 3t squared square root of 9t to the fourth plus 16t squared. So really, to take that shortcut, it's often helpful to take a look at the plane curve to determine exactly what direction the unit normal vector should point in. Let's go and take a look at one more. When t is equal to pi over 4, we want to determine the unit normal vector. And before we find the unit normal vector, we have to determine the unit tangent vector. So let's start here on the left. So the derivative of cosine t would be negative sine t. Derivative of sine t would be cosine t. The derivative of t would be 1. We'll divide this by the magnitude. So negative sine squared would be positive sine squared t plus cosine squared t plus 1. Well, sine squared t plus cosine squared t is equal to 1. So we'd have the square root of 1 plus 1, or the square root of 2. So our unit tangent vector valued function would be negative sine t divided by the square root of 2, cosine t divided by the square root of 2, and 1 divided by the square root of 2. Now, since the unit tangent vector is going to have 3 components, we won't be able to take a shortcut on this one. So now we'll have to determine the derivative of this vector valued function and then divide by its magnitude. So let's go ahead and do it. So the derivative of negative sine t divided by the square root of 2 will be negative cosine t divided by the square root of 2. Then we'll have negative sine t divided by the square root of 2. And the z component will be 0. We divide this by the magnitude of this vector valued function. So we'll have the square root of the square of the x component. That will be cosine squared divided by 2 plus sine squared divided by 2 plus 0. Let's take a look at this denominator. We'll have cosine squared t plus sine squared t divided by 2. Well, cosine squared t plus sine squared t would be 1. So this will be the square root of 1/2, or 1 divided by the square root of 2. Now when I rewrite the vectored valued function in the numerator, I'm going to go ahead and factor out the 1 over square root 2. It's going to give us negative cosine t, negative sine t, 0. Notice that this simplifies nicely. 1 over square root 2 divided by 1 over square root 2 simplifies out. So we have the unit normal vectored valued function is equal to an x component of negative cosine t, a y component of negative sine t, and a z component of 0. So then when t is equal to pi over 4, we're going to have negative square root 2 over 2, negative square root 2 over 2, and 0 for the z component. And to finish off, let's go ahead and take a look at this graphically. We have our space curve in blue, our unit tangent vector in red, and our unit normal vector in purple. Let's animate this to t equals pi over 4. Pi over 4 is approximately 0.785. So let's go ahead and move it to that value. It's about in here, and again we can see that those two vectors are orthogonal to one another, and they also both have a magnitude of positive 1. Remember, we found the unit normal vector, which is the purple vector here. Okay, that's going to do it for this video. I hope you found these two examples helpful.